Welcome to this lecture on modular arithmetic and congruences. If you have ever looked at a clock to tell the time, you already intuitively understand the core concept we are going to discuss today. In this session, we will formalize this everyday intuition into a rigorous algebraic framework. We will learn how numbers can wrap around a maximum value, how to write these relationships mathematically, and why this seemingly simple idea is the absolute bedrock of modern digital security. Let us dive in. To begin our journey, imagine you are looking at a standard analog wall clock. If the current time is 10 o'clock and you wait exactly 5 hours, you do not say it is 15 o'clock. Instead, the hour hand sweeps past the 12 and lands on the 3. The numbers on the clock do not go on forever to infinity. They reset or wrap around every time they reach 12. This everyday concept of wrapping around a certain limit is the heart of modular arithmetic. In mathematics, we call this limit the modulus, which is just a formal way of saying the wraparound point. Now that we understand the basic idea of a clock, let us formalize this in algebra. We say that two integers are congruent modulo n if they leave the exact same remainder when you divide them by n. The word congruent here just means equivalent in this specific system, and modulo tells us what our wraparound number is. For example, 15 and 3 are congruent modulo 12 because dividing either of them by 12 leaves a remainder of 3. They behave identically within our specific wraparound system, even if they are completely different on a normal number line. Let us look at how we write this mathematically. We write this relationship using a special symbol with 3 horizontal lines, which looks like an equal sign with an extra bar. The formula is read as A is congruent to B modulo n. Conceptually, this comes directly from our remainder definition. In this expression, A and B are the two numbers we are comparing, and n is the modulus, which must always be a positive integer. If you increase the number A by exactly n, the congruence remains perfectly true, because adding the wraparound value does not change the final position on our imaginary clock. This formula we just saw leads us to another incredibly useful way to define this relationship. If A and B leave the same remainder when divided by n, then the difference between A and B must be a perfect multiple of n. We write this as n divides A minus B. The vertical bar is mathematical shorthand for divides evenly into, with zero remainder. This is the most powerful tool in modular arithmetic. To check if two numbers are congruent, you just subtract them and see if the modulus divides the result evenly. If the modulus n gets larger, the distance between congruent numbers must also get larger. Before we prove why this subtraction method works, let us see it in action with a concrete example. We are asked to determine whether the number 38 is congruent to the number 14 modulo 12. This is exactly equivalent to asking if 38 hours and 14 hours point to the same spot on a clock. We will use the subtraction definition of congruence. Instead of dividing both numbers by 12 and comparing their remainders, we will simply subtract 14 from 38. This gives us a difference of 24, representing the total distance between the two numbers. Continuing with our calculation, we now need to check if this difference is a multiple of our modulus, which is 12. We can clearly see that 24 is exactly 2 times 12. Because 12 divides 24 perfectly with absolutely no remainder left over, the condition for congruence is fully satisfied. This means 38 and 14 land on the exact same spot on a 12-hour clock. This subtraction method is often much faster than doing two separate long division problems, and it gives us a clear physical meaning of the distance between the numbers. Now that we have successfully used this subtraction formula, let us understand exactly where it comes from. We want to prove that if two numbers have the same remainder, their difference is a multiple of the modulus. We start by writing out what it means to divide A and B by n using basic division. We write A equals Q1 times N plus R, where Q1 is the quotient and R is the remainder. Similarly, B equals Q2 times N plus R. Notice that we use the exact same letter R for the remainder here. Keeping the variable identical is the crucial step that makes the whole proof work. Moving forward with our subtraction, we set up a simple algebraic equation to see what happens to the difference between A and B. By substituting the expressions we just built, we subtract the two equations. When we perform the subtraction, the positive R and the negative R completely cancel each other out, leaving zero remainder. We then factor out the common modulus n. Because Q1 and Q2 are both whole numbers, their difference is also a whole number. This proves that A minus B is exactly equal to some integer multiplied by n. This gives us our final result, proving that n perfectly divides the difference. So we have proven our subtraction rule. This brings us to another practical challenge, dealing with large powers. We are asked to find the remainder when 4 cubed is divided by 7. Calculating large exponents can result in massive numbers that are hard to divide. The beauty of modular arithmetic is that we can apply the modulus at every single step of multiplication to keep the number small. We start by calculating the first part of the exponent, which is 4 squared. This gives us 16. We are taking a small step first to avoid dealing with the full power of 3 immediately. Continuing with our exponent problem, instead of multiplying 16 by 4 right away, we shrink the 16 using our modulus, 7. Since 7 goes into 16 twice with a remainder of 2, we can replace the 16 with a 2. We have effectively reset the clock early. We now write out the original problem, 4 cubed, as the product of 4 squared and 4. This is a basic rule of exponents. This allows us to substitute the smaller congruent value we just found. By doing this, we prevent the numbers from growing out of control. Let us wrap up this calculation. We replace the 4 squared with the 2 we found in the previous step. This substitution is completely legal because 16 and 2 behave identically in a modulo 7 system. We multiply the simplified numbers together and the result is 8. Which is a very small, manageable number. Finally, we apply the modulus one last time. When we divide 8 by 7, the remainder is 1. Therefore, the final remainder is exactly 1. By shrinking the numbers at each step, we avoided dealing with large arithmetic entirely. To truly cement what we just calculated, let us visualize this wraparound effect. This diagram visually summarizes how numbers wrap around in a modulo 7 system. You can see a clock face with numbers 0 through 6. Just like the hands on a clock, counting up to 9 means completing one full circle of 7 steps and then taking 2 more steps. The blue arrow traces this exact path and the final resting place is 2. This perfectly illustrates why 9 and 2 are congruent modulo 7. It proves that no matter how large a number gets, it always maps back to a small fixed set of positions. You might be wondering why mathematicians care so much about remainders and wrapping numbers around in circles. The truth is, modular arithmetic is the invisible shield protecting your entire digital life. Every time you log into your bank account or send a secure message, your computer uses cryptography algorithms like RSA, which rely entirely on modular arithmetic with massive prime numbers. It is also used in computer science to organize data efficiently using hash functions, which sort information into digital buckets based on remainders. Without this simple concept of clock math, modern internet security would completely collapse. Let us bring all of these ideas together. We have learned that modular arithmetic is a system where numbers wrap around after reaching a specific modulus. Two numbers are congruent if they leave the same remainder, or equivalently, if their difference is a perfect multiple of the modulus. By allowing us to shrink large numbers down to their remainders at any step, it provides a powerful shortcut for complex calculations. You have now mastered the absolute bedrock of modern digital security. Great job, and keep practicing these concepts.